Hi, in this lecture I will go over some examples of dry friction. Example 1 that I have is asking to determine the smallest coefficient of static friction at both A and B needed to hold the uniform 100-pound bar in equilibrium. Neglect the thickness of the bar. Okay. The first thing that I understand from this problem, and the keyword that I look for, is this one: at both A and B needed to hold the uniform 100-pound bar. So I have to approach this problem with the idea or assumption of impending motion at both A and B, both points of contacts. All right. Now I got to draw a free body diagram. First step. So let's see. Step 1, free body diagram, is drawing the outline of the shape. I'm drawing free body diagram of beam AB and or AC, whatever it's called. This is the outline. Then put active forces. The only active force that I have is the weight, which I put it in the center. And next one is reactive forces. I have 2 points of contact. Both of them are smooth contact, as we know. We've practiced this before in rigid body chapter. So I have normal force A. You can call it whatever you want. You can call it AY. We used to call it AY, but in this chapter it's preferred to call it normal force because we're going to use them in friction. And there's another point of contact at B, always perpendicular. So that one, I call that normal force at B. Okay. This one, the slope triangle for it is 12, 5, and 13. Okay. Now, let's see. Find the smallest coefficient of static friction at both A and B needed to hold the uniform. So, if this friction is not there, which I haven't put on the free body diagram yet, this bar is gonna slip, move this way. So point A is going to move this way, motion, if there's a big F. And point B, motion, is going to be right there. The motion and the direction is important, the sense of direction, because I need to figure out the friction force. Okay? So there is going to be a friction force at point A that is holding this beam, and it's going to be opposite direction to the motion. So I call that friction of point A. The other one is friction at point B. If point B is going to move in this direction, then the friction needs to be going this way. Friction at point B. The slope triangle for that force is opposite of the other one. 12, 5, 13. Okay. Friction always opposite of motion or potential motion, and it's always tangent to those contacting surface. At point A, I have like this, and the beam is kind of like this, like magnified. So these two contacting surfaces are right there, so the friction is tangent to that. At point B, same thing. I have this, I have that. Tangent to these contacting surface would be in this direction. All right, and I think that's all I have for free body diagram. Let's see, this 100, the slope triangle for that one should be 5 this way, 13, and 12. All right, so now I'm going back to my rigid body analysis, same as before. The unknowns that I have are FA, FB, NB, NA, and mu s. Okay, I start with summation of forces, summation of moments about point A being 0. I'm going to go through this really fast. If you still have questions about rigid body analysis, you gotta go to previous chapters. Okay, so this analysis that I'm writing, the equations I'm writing, is just the rigid body analysis. I have NB, the perpendicular distance. This NB is perpendicular 90 degrees, so that distance is 13 feet, and that is plus. I have 100. The only component is this component, which is going to be 112 over 13 at a distance of half of that distance, half of 16, which is 8 feet, and that one is minus equals 0. So I get NB of 56.8 pounds. Okay. Next, I'm going to write summation of forces in X being 0. FA, which is plus 100 is just vertical. NB, the X component of it is going to be 5 over 13, and that's negative. And then I have FB, the X component of this, which is plus, is going to be 12 over 13 equals 0. NB I already found to be 56.8. I still have two unknowns. Summation of forces in Y direction being 0. I have NA minus 100 plus the vertical component of NB, which is 12 over 13, plus vertical component of FB, which is 5 over 13 equals 0. NB is 56.8. I still have FB and NA. Okay, now I go back, look at this information that I have from the problem. Okay, I will have slipping at both, impending motion at both. So I can say FA equal mu, let's just call it mu, NA, and FB is mu NB. NB I have it 56.8, so it's mu 56.8. So if I replace all of FB's and in these two equations, I'm gonna go next slide. From equation 1 and equation 2, and replacing FA mu NA and replacing FB mu 56.8, I will get an equation that looks like this: 100 mu minus 21.85 mu 2 minus 21.844 equals 0. And if I solve this equation, I will get mu of equal 230. What is the unit for coefficient of static friction? No units, because this is newtons, this is newtons, or this is pounds, or this is pounds, so mu doesn't have any units. So now that I have mu, smallest coefficient of static friction, that's all I wanted. But you can go back, remember I had all of these unknowns. You can go put back 2, 3, NA. You can put this as 0.23, 56.8 pounds, and so on, and find all of the other unknowns that we had. 425.2, 9786, 1307, NB we already had it be 56.8, and mu was 0.23. Just as extra practice, this is how we can find all of the unknowns. Okay, let's look at another problem. Beam AB has a negligible mass and thickness and supports 200 kilogram uniform block. It is pinned at A and rests on the top of a post having a mass of 20 kilogram and negligible thickness. Determine the minimum force P needed to move the post. The coefficients of static friction at B and C are this much and this much, respectively. Okay, so let's see. There are, if we start pulling at point P, there are 2 points. This is one of them, this is the other one. But from the problem, I cannot figure out which one is going to move first, or if they are going to move together. So I don't know. So this problem, this is not clear which one is going to move first. Okay, so the way to work is I just work my problem the normal way without using the equation of friction, and then I have to figure out if one of them moves before the other one, or I have to just assume for one of them and do it. Okay, so let's start with free body diagram. Free body diagram, I will divide this into 2 members. So this kind of looks like a frame. Okay, so one is A, B, the other one is B, C. Okay, let's start with AB. Put the active forces first, which is that block has 2 kilogram mass, so it has 209.81 newtons. Point A is pin, so I'm going to put AX and AY. Point B is a smooth contact sitting on another post, so there is a normal force B. So let's see. If I want to figure out which direction the friction is working, okay? This is too difficult for me. I cannot figure it out. So let me go to BC first. It's easier for me. Once I figure out the friction on that one, I can come back here. It's just like when we were analyzing frames. They are the same point. This point is B, same as this point, which is B. So they should have equal and opposite forces. Okay, so let's look at point BC. Active force, IC1 P, which is 435. Point C and B, they're both smooth contact points, so there is a normal force at point C. There is a normal force at point B. All right, if the motion or impending motion located for BC, so impending motion, if I pull force P, impending motion is going to be in this direction. So for both C, the friction is going to be opposite of that, and it's the same beam, so friction for this one also going to be opposite of movement. All right, now that's a little bit easier. Now I can go back to AB and put opposite forces of friction on there. So remember, exactly like frames, when you put these 2 points back together, the forces should cancel each other out. All right, I have way too many unknowns. Let me write them down. I have NB, NC, FB, FC, AX, AY, P. 1, 2, 3, 4, 5, 6, 7 unknowns. It's actually too much. So let's see. Let's just start with our equations. Summation of moments about A being 0. Again, I'm going through these really fast. NB 3 meters minus 209.8 is 1962 equals 0. I get NB of 9.81 newtons. Okay. At least I got one of them, 9.81 newtons. Then let's see. From Freebody diagram of BC, I'm going to write summation of forces in y direction being 0. I have plus NC minus NB minus, what am I missing here? Oh, this also weight. This is also 200 kilogram weight, so I missed that one on my free body diagram. There we go. W equal 29.81 newtons. So minus newtons plus vertical component of P equals 0. The only thing I have is NB is 9.981. Let's write summation of moment about point C being 0. I have FB, the distance of 1.75 meters. I have the horizontal component of P at a distance of 0.75 meters. And that's it. NB and NC and that W, they both go through it, so 0. Summation of moment about point B equals 0. I have minus FC at a distance of 1.57 meters plus the horizontal distance at 1 meters equals 0. I have NC, FB, FC, and P as unknown in these three equations. Okay, so now what? Now I have to go back to my friction assumptions. So let's assume if, it's a big if, C moves, or if it wants to move first. Remember, nothing ever moves. We only get them to the point of impending motion. Okay, so if C is in impending motion, meaning C impending motion, then I can say for point C, because it's at impending motion, FC is mu C NC. Mu C, the problem tells me that it is 0.2 NC. All right. So now I got to put it back into the equation. So FC equals 0.2 NC. Then how many unknowns do I have? FB, NC, and P. I have 3 equations, 3 unknowns. I should be able to solve it. If you solve those equations, you're going to get NC 932, FC 186, FB 140. Okay, so I got one value. But I was assuming, maybe I was wrong. What if I was wrong? So that means I have to check. So now I have to check to see if my assumption was right or wrong. Okay. And here's how you can check it. If B moves first, okay, before point C, that means force B would have been mu B NB. NB, I found it to be 981.4981 would be 392.4 newtons. Okay. So if B wanted to move first, I would have got FB of this much. If C moves first, what did I get for FB? 140. So FB of C moving 140 newtons. FB of B moving, I got 392. This one is way bigger. So that means that B will not slip first. And that means my assumption was correct, that C will move first. So then I can take all of these forces as my correct answer. Here's another way that you can check. I assume that if C moves first, I use this equation. Okay. You can take another assumption, says, hey, I assume if B moves first. And use this equation that I had. Use FB and do not compare it. Okay. Go back and put them in these three equations that I had. For that, you're going to get a set of answers too. FC and FB, which you already have. But I promise you, if you do that, your P is going to be much larger. I don't know how much. It's going to be, I can't guess, but it's going to be, let's say, 1,000 newtons. Okay. So now you have two assumptions. You have assuming that if C moves first, you need this much, meaning P of 408 will cause C to move or slip. P of 1,000 is needed or required to slip happens at point B. Let's go back, look. So I start pulling here. When my force P is at 408, C start to slip. When my force reaches 1,000 newtons, which is not possible anymore because C is already slipped, then B starts to slip. So when you look at that, which point do you think will slip first? So that also proves that, hey, my assumption was correct. So for problems like this, you can go with either way. You can make an assumption and find two sets of data, set 1, set 2, compare them with each other, and whichever has lower force, that will be your answer. Or the way I did it here, you can make an assumption and just check that assumption to see whether that was correct or that wasn't. Okay, let's look at another problem. Determine the minimum applied force P required to move wedge A. That's a new word for us. To the right. The spring is compressed a distance of this much. Neglect the weight of A and B. The coefficient of static friction for all contacting surfaces is this much. Neglect friction at the roller. The first thing I want to tell you is wedge is a type of machine. Why, you might ask, is because it transfers forces or force into a much larger force. If you remember from previous chapters when we were discussing frames and machines, that's what machines do. We use machines to transfer forces and use them to increase the forces. So for a problem like this, I have to draw a free body diagram of A and B with friction forces on them and analyze each of them. Okay, let's start with the B. Isolate. Put active forces on it, which I only see a compression that comes from a spring. Which is how much? Let's see. I have the stiffness of a spring, 15 kilonewtons per meter. And it is compressed 0.175 meters. So I will get 2625 kilonewton force of a spring. Remember, force of a spring was spring constant multiplied by amount of the formation. Which is initial length minus current length. Here it just tells us that, hey, this is compressed this much. So X is given. All right, so that was that. Point between A and B, there is a contact, NB. When I move wedge A, there's going to be a friction. Again, this is a little bit difficult for me to figure it out right now, so I'm going to go draw a free body diagram of wedge A. Whatever friction I find on there, I'm going to put opposite direction. Before doing that, there is a normal force from rollers also. Let's put that on there. Okay. For wedge A, so let's see. Top part is right there. There we go. Okay. Active force, force P. And then there are two contacts. There is one between the wedge and lower surface, and there is one between the cylinder B. I have, let's call this one normal force A. The other one going to be normal force B. Okay, now I have friction. So if P is pushed, impending motion, or just motion, which way it's going to be? It's going to go this way. Friction is opposite, tangent to each of those surfaces. So I have a friction B, I have friction A. There we go. Now that I know friction B is going this way, on the other one I have to put it opposite direction. So it's still tangent, I just draw it a little bit lower to avoid confusion. Okay, again, look, these 2 points are the same point. When I put them back together, they should cancel each other out. Okay, so what kind of problem is this as far as impending? So let's see, when wedge starts to move, it would be impending motion at both of them because this wedge is going to move. So at both surfaces, we have impending motion. So impending motion at both A and B, at both surfaces. I'm going to use that later. So let's see. For B, let me write summation of forces in y equals 0. I have minus 2.625 kilonewton plus NB equals 0. So my NB is 2.625 kilonewton. All right. 2.625. So let's write summation of forces for A right away. So for A, summation of F forces in y being 0, I have minus NB, 625, and then NA has the angle of, how much is that, 10 degrees, plus NA cosine 10 degrees. And don't forget, this friction force is going to have also a vertical component. FA, that is going to be sine 10. Okay. Minus FA sine 10. All right. I have NA, impending motion at both. So it is fair to say FA is equal 0.35 NA. Where did I get that? Right there. So if I do that, 0.35 NA, the only unknown here is NA, so I can find NA to be 2.841 kilonewtons. Okay, 2.841. All right. So when I know that, that means I know FA. So let's write summation of forces in x direction for this free body diagram. I have P minus FB, which is 0.35 NB, minus FA, 0.35, 2.841, and the only other thing left is the x component of NA, which is minus 2.841 sine 10 equals 0. The only unknown here is P, and I will get force P to be 2.39 kilonewton. So as you can see, it's really important to figure out what points are going to be impending motion, because that will provide additional equations for us. So for a problem like this, both of them were about to move at the same time, so both were at impending motion. Next example are two blocks sitting on top of each other and connected by a rope. The coefficients of frictions are mu s this much, mu k this much between all surfaces of contact. Find or determine the smallest p required to start the 30 kilogram block moving if cable AB is attached, B, cable AB is removed. All right, so let's focus on case A first. So the coefficient of static friction, so first of all, I don't care about that because I analyze the stuff. Remember, smallest p. If you remember from the graph that we had, this p is impending motion. That is the smallest p. because anything after this point is larger than that P. So impending motion is always my smallest P that will start. See that start means impending, the 30 kilogram block moving. So we want B to move if cable AB is attached. Cable AB is attached, so I have to draw two free body diagrams here. One for block A, one for block B. So let's start with block A. Block A, draw the outline. I have weight of block A, which is 20 kilogram, 9.81, 196.2 newtons. It is attached to a cable. Cable is always tension, like that. And it has a normal force because it's contacting another surface. So it has a normal force, which I don't know what to call it. Let's call it normal force A. Sorry, normal force 1. And there is a friction. But I honestly don't know which way the friction is going. It's too difficult for me. So let's do block B, and I promise you will figure out block A next. Block B has a weight of 30 kilogram. So WB which is 30 kilogram, 9.81, should be 294.3. Okay. It has a normal force from A and 1. Remember, these 2 points are the same, right? When I put them back together, it should cancel each other out. And it has another normal force because it's a contacting below also, this way. So it has one normal N1 because it's contacting A. It has weight, and it has N2 because it's contacting the ground. It has a force P going this way. It has a force T going that way. I've seen a lot of people put T1 and T2, and then there are too many unknowns, they can't do it. Remember, this is the same rope. Same rope, so it has the same tension all over. So they're both T1. All right, now friction. If block B starts moving, so motion is going to be this way. So friction is going to be opposite of that. So I have one friction here, F2. I have one friction here. I have F1. Okay, this block is moving entirely to the left, so both of the friction should point towards right. Now that I have this F1, the other one is easy to figure out. The other one needs to be opposite direction of it. So this is one way of figuring out friction direction. See, the one that is more obvious, which is block B, it's easy to figure it out. Figure that one out first, then go back and put it on the second one. Or you can find relative movement. So block A is not going anywhere, right? Block B is going to the right. So block B going to the right, it makes block A going, or sorry, block B is going to the left, block A is going to the right. So if block A is moving to the right, then the friction should be opposite, and that's what I figured out. Okay, so we have these two equations, or sorry, free body diagrams. Now let's start solving for the unknown. The goal was to find force P, remember. Okay. This one, let me write summation of forces in y equals 0. Then I get N1 being 196.2 newtons. 196.2. Okay. Summation of forces. Let me see. Summation of forces in X being 0. So T minus F1 equals 0. If block B starts moving, block A starts moving too. So it's impending motion for both. So I can say F1 is mu N1. And mu is given to be 0.4. In other words, T should equal 0.4. N1 is 196.2 newtons. T1 turns out to be 78.48 newtons. Okay, 78.48. All right, so now I move on to block B free body diagram. I have, again, summation of forces in Y being 0. I have 196.2 minus 294.3 plus N2 equals 0. N2 turns out to be 490.5 newtons. Let me tell you something. A lot of people ask, well, block A is sitting on top of block B. So when we draw free body diagram of block B, shouldn't we add weight of block A because it's sitting on top of it? The answer is no. Because, first of all, you're drawing free body diagram of B. You do not care what happens elsewhere. Second, look at this N1. So what do you think that N1 is? N1 is the effective weight of block A on block B. So you've already considered it because it's in contact with another block. So the answer is no, you don't need to put weight of block A on top of block B. It's already there. And the last equation that I'm going to use is summation of forces in X being 0. I have P minus F1, which I already know, minus F2 minus T equals 0. T, I already have it. F1 is mu N1. I have that. F2 is also 0.4, mu N2, 490.5. The only unknown here is P, and it's going to result in 353.2 newtons. Okay, that was all that work was part A. Cable AB is attached as shown. Part B says if cable AB is removed. Cable is removed. So if I get rid of this cable, this whole thing, then two blocks are sitting on top of each other and force P is moving it to the left. I can just simply draw outline like this. Put force P going this way. Now the weight is added together. So it's weight of A plus weight of B all added together, which is going to be 490.5 newtons. I have a normal force, which I have to draw it a little bit offset, remember, because of that moment, but it doesn't matter. Normal force, I just put normal force. Motion is to the left. Friction is going to be opposite. Just put F. Very simple. All I have to do is write summation of forces in X equals 0. So minus P plus F equals 0. And I don't know F, so I gotta write summation of forces in Y equals 0. So minus 490 newtons plus N equals 0. So I get N of 490.5. It's kind of confusing, but this is newtons. The other one is variable and normal force. Once I know that, impending motion, I can write 0.4 mu n. This is my friction force. This is going to be 196.2 newtons. So put it back in this equation, 196.2. Therefore, P is going to be 196.2 Newton. Okay. So that is this problem. Let's look at another one, which is similar, just a little bit different. Okay, each box weighs 10 pounds. Coefficient of static friction between box A and box B is this much. Coefficient of static friction, so let me just write it here. Mu here is 0.24. And mu here is 0.3. Okay. Mu1, mu2. Just so I remember. What is the largest angle alpha for which box B will not slip? Okay, or in other words, what is the largest angle alpha that put box B at impending motion? Okay, the same thing, different ways. The point that I want to make with this problem is to teach you a technique that sometimes you can rotate your axis and save a lot of trouble. Let's see. Freebody diagram. Block A. Each has 10 pounds. So it has a W of 10 pounds. W is always a straight down. It is attached to a cable. Cable ropes are always in tension, meaning going away. It is contacting another block. Contact always has a normal force perpendicular to the surface. And it has a friction. Okay. Again, this is kind of difficult for me to figure out the friction. So let me go draw Freebody diagram of B, and then I'll get back to A. B has a weight of 10 pounds. It is contacting A, so there's always a normal force. It is contacting the slope. There is a normal force there. And now there's a friction. So let's see. If I raise this angle alpha, what happens? Block B eventually is going to move down, or it's going to start or reach to the impending motion. Motion being this way, friction needs to be opposite direction. So I'm going to have, let's call this FB, let's call that FA. Once you figure one friction, the other one is opposite, FA. So this is the best way to figure it out. First, find the more obvious one, go back and put it on second one. Or, as I just mentioned in previous problem, relative movement. A, B. If B is fixed, or B is going this way, it is as A is moving to the right. This is relative motion. Therefore, the friction needs to go the other way. Relative motion is a little bit more challenging to find. It works only if you have a very good imagination and you can keep track of which one is going where. If not, this option that I did it here is a much safer way of doing it. Find the obvious one and go back and put it on the second diagram. So the rest is similar to the previous problems, but the one I want to mention here, one trick that I want to teach you is, for problems like this, always rotate your axis. Okay, some people call it x prime, y prime. I just like to keep it x and y. Okay, because now look, FA, NA, T are all in x or y. You have only one angle to transfer. So let's see. If I write this, summation of forces in x equals 0. This way is positive for me. Then I have T minus F A B. What did I call AB? Oh, okay. AB, it's right there. Yeah, could have just called it A. That's fine. Minus the x component of that weight, 10 sine alpha equals 0. Summation of forces in y equals 0. This way being positive. I have NA minus 10 cosine alpha being 0. For B, I have to say, same axis, summation of forces in x being 0, this way being positive, FAB plus FB minus 10 sine alpha being 0. Summation of forces in y being 0. NB minus NA minus 10 cosine alpha being 0. Okay. And the motion or impending motion is going to happen at both of these at the same time. If block B starts to slip, both of the surfaces are going to have. So FAB, I'm going to replace it by 0.24 NB or NA, sorry. FA or FB, I'm going to replace it by 0.3 NB. Okay, if you do this equation and you find all of the unknowns, the alpha is going to be 40 degrees for